Hello everyone. In this video, I'll discuss about some uniform continuous charge distributions. If the charges are distributed continuously and uniformly over a line, then we call such charge as line charges. In the same way, if we have charges which is distributed uniformly and continuously over a surface, we call it as surface charge. And likewise, if throughout a volume, if the charges are uniform and continuously distributed, we call such charges as uniform volume charge distribution. For such charges, let us discuss what are the measure of electric field intensities and how to make it. If we consider over a length, the charges are distributed uniformly and continuously, it is possible to get what is the charge per unit length. That is defined as line charge density, which is the charge per unit length of this charge. We can mathematically represent as rho L, and it is given as charge Q per unit length if the length is very small. It is measured in the units of coulombs per meter. With this charge density, it is possible to get total charge contained in the entire length of this charge. That is, total charge can be written as integration of this line charge density value over the length of this line. Similarly, for a surface charge, if it is continuous and uniform distributed, we can define charge per unit surface area, and that is called surface charge density, which is indicated as rho suffix s. Whereas it is by definition charge per unit surface area, and it can be written as charge per unit surface area if the surface area is very small with the units of coulomb per meter square. With this surface charge density, it is possible to write total charge contained in the entire surface area of the charge, which is surface integration of charge density over the surface. Likewise, we can give the charge density for a continuous uniform volume charge where it is the charge per unit volume. Mathematically, Q by del V if del V approaches 0. And with this volume charge density, which is having the units coulomb per meter cube, we can find the total charge contained in the entire volume of the charge, which is done by evaluating volume integration of this charge density over the entire volume. Now, let us discuss about how to apply this Coulomb's law to find electric field intensity for different types of charge distributions right from point charge. If we consider a point charge Q and at a distant point P, where we consider this as the observation point, we find electric field intensity. We aim to find electric field intensity at this observation point. For simplicity, let us consider this point charge Q is present at the reference origin. Now, in this case, we are going to follow rectangular system of coordinates and use Coulomb's law to get the expression for electric field intensity at this faraway observation point. We have already discussed about the electric field intensity expression in the previous video. That is Q by 4 pi epsilon vector R divided by magnitude of that R cubed of it. So we have to first find what is the displacement vector from the charge point to the observation point P. So that we have to find. If we consider in rectangular system, the distance of observation point P is at x in x coordinate, y in y coordinate, and z in z coordinate, then the vector R can be written as x ax cap plus y ay cap plus z az cap. And likewise, we can find the magnitude of vector R from this expression of vector R, which is under root x square plus y square plus z square. And putting these two into the expression for electric field intensity from Coulomb's law, we get electric field intensity at a faraway point P due to a point charge Q, where the charge Q is located at origin. Next, We are going to consider the other coordinate system for the same scenario to find the expression for electric field intensity so that we will have a better understanding of which coordinate system is simpler to solve this case of example. If we consider a spherical system of coordinates, the point P will be represented with the coordinates of radius of the sphere and elevation angle theta and also the azimuth angle phi. If we follow the same assumption as the charge q present at the reference origin and the observation point P is at a distance of r and at a specific angle of theta and azimuth angle of phi, we can apply the expression for electric field intensity from Coulomb's law. But when we look at the point P and the charge Q, the point P is having or the charge Q is having symmetry with respect to the observation point. Or when we move around the charge Q at a same radius, when we move around the charge Q through the elevation angle or the elevation plane, the charge appears to be symmetric, appears to be same from the faraway observation point. So it is said to have symmetry about the center and it is having symmetry in theta plane. Similarly, when we go around the azimuth angle, in the direction of azimuth angle, there also the charge q appears same from the faraway point P. But the only difference will be when we move in the radius far away from the charge q, then when we move farther and farther, the charge q appears to be smaller and smaller. So when the point P is moved in terms of r, then the magnitude of electric field intensity is going to change. When we move around the charge q in the elevation plane and also in the azimuth plane, the charge is appearing same and the magnitude of electric field intensity remains same with a constant radius of r. So we can say this type of system exhibits symmetry in two planes, in theta plane and phi plane. Thereby, when we find the vector r from the charge q, which is said to be at the origin and at the observation point P, the vector r will have only the component which is r direction component and the distance is r from the origin. We can find magnitude of this distance vector as r. Substituting these two into the expression for electric field intensity from Coulomb's law, we'll get the electric field intensity due to a point charge q at a faraway distance r. Now, when we compare the expression for electric field intensity obtained with rectangular system and spherical system, spherical system appears to be simpler with this kind of symmetry problem. And when we solve for any electrostatic field problems, we will look at the symmetry and choose the proper coordinate system for simpler solution. Next, let us discuss about few general steps which we will follow to solve for electric field intensity using Coulomb's law for different types of charge distributions which are continuous. Starting from a line charge, if we have a line charge and an observation point P is where we are measuring the electric field intensity, first we need to find what is the small amount of electric field intensity, that is the differential amount of electric field intensity produced by a smallest length element in this line charge. And we will take integration of or evaluation of electric field intensity summing up over the smallest length elements throughout the line charge. That is the integration of the small dE throughout the length at this point P will give the total electric field intensity contributed by the entire line of charge. Starting with computing what is the smallest length element, then we can find how much of charge is contained in the smallest length element with the help of known value of charge density. And we can find what is the displacement vector of the observation point P from the charge. And we can apply Coulomb's law to find the smallest amount of electric field intensity produced by the smallest length element. Then we can integrate the value of differential electric field intensity over the entire length of the charge to get the total electric field intensity's contribution by the length of the charge. Similar approach can be done for surface charge, where we will consider a small surface area, which is a differential surface area on this larger surface. We'll find the contribution of electric field intensity due to this smallest surface element. Then we will integrate over the entire surface area. First, we will estimate ds. Then we will find what is the charge contribution in the smallest element ds with the known charge density. Then we will find displacement vector r. Then apply Coulomb's law. Then find electric field intensity by performing surface integration. Similar approach can be done for a volume charge, where we will consider a small volume element and we will estimate the charge contained in that volume element with the help of the known value of charge density. Then we will find the displacement vector r. Then we can apply Coulomb's law to find the differential amount of electric field intensity. With this differential amount of electric field intensity, we can find the total electric field intensity contribution by the entire volume of charge by doing volume integration of this dE vector. We will discuss about the derivations of electric field intensities due to line charge, surface charge, and volume charge in further videos. Thank you for watching.